Welcome to Spring LIB.
This question begins with the percent carbon and hydrogen that is cyclopropane. And it wants you to figure out what the molecular formula is. To do this, we need to know the mass of cyclopropane and the moles of cyclopropane. The moles we can calculate from the ideal gas law. Let's take this one step at a time. First, knowing the percent that is carbon and hydrogen in cyclopropane, we can calculate the empirical formula. If we have 100 grams of cyclopropane at 85.7% carbon, we would have 85.7 grams of carbon. We can convert these grams of carbon into moles of carbon, and we get 7.136 moles of carbon. The rest then is hydrogen. So 100 grams, we would have 14.3 grams hydrogen, which we can also convert into moles hydrogen by dividing by the molar mass of hydrogen. So now we know the mole relationship. For every 7.136 moles of carbon, we have 14.19 moles of hydrogen. Dividing by the smaller number, this gives us a 2-to-1 ratio. So for every 1 mole carbon, we have 2 moles hydrogen. This will be the empirical formula, CH2. This empirical formula has a molar mass of 14.027 grams. This will tell us, or this will be important in determining what the molecular formula is when we need to calculate the subscript multiplier. So now let's figure out what the molar mass of cyclopropane actually is using the ideal gas law to calculate moles and then using the mass that was provided. They tell us that when we add 1.56 grams of cyclopropane to a liter at 0.984 atmospheres and 50 degrees Celsius, that it ends up filling the container. So with this information, we can calculate the moles using the ideal gas law. Moles will be equal to PV divided by RT. The pressure they gave us was 0.984 atmospheres. We'll multiply that by the volume, which they gave us at 1 liter, divide it by R, 0.08206 liter atmospheres per Kelvin mole, multiplied by the temperature in Kelvin. They tell us it's 50 degrees Celsius, so we'll add 273 to that in order to get our Kelvin temperature. This then gives us moles of 0.03712. So to calculate the molar mass, we need to take the mass and divide it by the moles. The mass that corresponds to this moles was given to us at 1.56 grams. So 1.56 grams corresponds to 0.03712 moles. So this ratio will tell us the molar mass, 42.02 grams per mole. So if this is the actual molar mass corresponding to the molecular formula, and this is the empirical formula molar mass, the subscript multiplier is simply this ratio, 42.02 divided by the 14.027, and we get a subscript multiplier of about 3. So we need to multiply each of these subscripts by 3 to go from the empirical formula to the molecular formula. And we get a molecular formula of C3H6. Knowing that the molecular formula is C3H6 and that the molar mass is 42.02, if we compare that to argon, the molar mass is slightly greater than argon, which is around 40, and because there are a total of 9 atoms here, this molecule is likely larger than a single argon atom. So because it has a greater molar mass, it potentially has greater intermolecular forces, and because it is larger, then it has a larger volume. So with a larger volume and potentially greater intermolecular forces, it's going to deviate, its behavior is going to deviate more from the ideal gas law than argon would. And for the last question, part C, it asks, would cyclopropane fuse through a pinhole faster or more slowly than methane? Well, cyclopropane has a greater molar mass with more carbons and more hydrogens, and as we increase the molar mass, we decrease the rate of effusion. So it's going to effuse more slowly through a pinhole than methane would.